Hello everybody, this is Professor Algarra in Thermodynamics. Welcome to chapter number 1, Introduction and Basic Concepts. But before I start, I just want to go over some important things. By now, I only have a few students on Connect. I need everybody to get their books as soon as possible, as well as the access to Connect. If you have problem with it, or questions or doubts, you're more than free to reach out in order to clear those doubts and get the help you need. For week number 1, it's kind of easy, it's fine, because we're only going to cover a few concepts. But then moving forward, and I'm talking about next week, we will need the book. You need to read the book, you need to get into the concepts, and more importantly, you need to do your homework. So like I said, if you have any questions, just reach out to me, and then we'll talk about it. All right. So chapter number 1 is basically one of the easiest, but also one of the most important ones. I'm going to introduce you into topics and terms and definitions that are going to help you understand in a better way what's coming in chapter number 2, 3, 4, 5, 6, and 7. So I just want to say something very important. Thermodynamics is a class that needs time, okay? A class that needs, a lot of input from you and from me, okay? That if you have doubts, you have to reach out to me, but more importantly, you need to read the book, okay? This is one of the toughest classes you might find in your engineering path, and you need to put the time into it. If you wait until the last day to do homework and understand everything, that will not work, okay? Like I said in my welcome video, this is probably the 5th or 6th time that I've been teaching this class, and so far, no complaints. I'm always here for you, so make sure you reach out. All right, so let's start by defining essentials. Thermodynamics is the science of energy, and energy is the ability to cause changes. The name thermodynamics stems from the Greek word therm, which is heat, and dynamics for power. Okay, conservation of energy principle. During an interaction, energy can change from one form to another, but the total amount of energy remains constant. From experience, and not as a professor, but as a student, I can tell you that thermodynamics always will require to be read more than one time, okay? So if, for example, thermodynamics, what is thermodynamics is super simple, right? It's the science of energy, that's it. But then when you're reading more deeper concepts like the conservation of energy principle, you might have to read it twice. So during an interaction, any energy can change from one form to another, okay? But the total amount of energy will always remain constant. Okay, energy cannot be created or destroyed, and this statement right here, it's quite important, okay? So make sure you understand this, because this will help you to understand what's coming in the next chapter. So heat flows in the direction of decreasing temperature, okay? It will always go from a high temperature source to a lower temperature source. So like here, the hot coffee is at 70 Celsius, and then it goes all the way to the environment, which is 20 Celsius. So after, after some time, 5 seconds, 60 seconds, something like that, it will reach equilibrium, and therefore they will reach the same temperature, okay? But the heat always flows in that direction, from the higher temperature to the lower temperature, okay? Applications areas of thermodynamics. So to be quite honest with you, thermodynamics is everywhere, okay? Anything that relates an exchange of heat has thermodynamics in it. And not only that, when you're looking at materials where things are built, then you will realize that there's some thermodynamics analysis that had to be done beforehand, like the seat where you're sat right now. That seat was probably made of materials that had to be studied under some circumstances with temperatures and things like that in order to work properly with the stresses and strains. So all activities in nature involve some interaction between energy and matter. So it is hard to imagine an area that does not relate to thermodynamics in some manner. So Applications will go, from the health industry to automobile industry. It's basically everywhere. But as you go deeper into your degree, whether it's mechanical or chemical engineering, you will realize that thermodynamics is pretty much everywhere. In this class, guys, it's like the base of everything, pretty much. Okay, when you go to heat transfer, when you go to heat transfer in mechanical engineering, for example, you will need thermodynamics for sure. Okay, and I'm gonna go into something very important. So all of you already had, chemistry and calculus and classes like this one. So the units and dimensions are very important when we're talking about thermodynamics. One unit can mess up with your final result and therefore give you a wrong answer in an exam or something like that, and then it could affect your grade. So let's just start by defining dimensional homogeneity. So all equations must be dimensionally homogeneous. Okay, what does it mean? So pretty much, apples and oranges. So if you have an equation, right, that is working in pascals, every term of the equation has to be in pascals. So if you have x plus y plus z, it's equals to whatever, 0, okay? Then the units of x, y, and z, they have to be the same. So if you're working with, let's just call meters per second square, then y has to be meters per second square, and z has to be meters per second square. Oh, professor, what about if it's pascales? Well, the same thing. It has to be pascales plus pascales plus pascales in order to get your pascales, okay? Just remember that, because sometimes when people have like thermodynamic exercises, they're working in meters per second square, but then they don't realize that they have, some pressure in it, and then they have to do something to that term in order to convert it in an homogeneous matter, okay? For that, we're going to use the unity conversion ratio. So sometimes when you have, for example, newtons, right? Newtons can be subdivided in kilograms per meters, meters per second square. The same thing if you're working with international system. Okay? So when you have non-primary units such as pascales, right? I mean, when you have something different than pascales or newtons, you might wanna, convert newtons into this, which is the same thing. So you can play around with kilograms, meters per second, and you can start cancel things out. Okay, this is very important for any engineering class, but for thermodynamics is, one of the most important things. So, always check the units in your calculation. Every term in an equation must have the same units, okay? That's very important. I already said that. All right, and then we need to start defining important terms such as systems and control volumes. And these ones are going to be used in chapter 2, 3, 4, 5, and pretty much in your whole engineering career, okay? So your system is pretty much a set of components or things that need to be studied, okay? So if you are, let's say, studying how, let's put this example. So we have a pump with water, and the pump is water. It's pumping water from the ground to some other place. And I'm studying exactly the phenomenon that is happening in the pump. I want to use dotted lines. So the system will be whatever component I'm studying. In this case will be the pump, right? Then we go with the next one, which is the boundaries. The boundaries will be what define the limits of my system. And those boundaries are going to be the little dotted lines that I put around the pump. Then the surroundings will be everything that is happening outside the pump. Therefore, you will study the interactions between your surroundings and your system. But now let's say you want to get a little bit more complexity. Now we have the system right here where the water is being brought, right? A piston and cylinder. and I'm gonna say that my whole system is the pump and the piston at the same time. I don't want to tell you more because I'm just going to confuse you, okay? But as far as for now, and like I said, these terms are gonna be defined more over and over again, and you're gonna get it, okay? But the system as it is the things that you're studying, okay? In my example was the pump. In your example could be something else. If the exercise is giving you more components or more cases, then we'll define those. Right after we have the system defined, then we can start establishing the boundaries. The boundary will be the limits of my system. And finally, the surroundings is what is outside the system. And now we're gonna take a look at this picture right here. Figure 119, that's on your book. Mass cannot cross the boundaries of a closed system, but energy can. So you have a closed system. Why is this system defined as closed? Super simple. It's perfectly sealed, and there's no mass coming in or coming out, and therefore your mass is constant. That's why your system is closed. You have energy coming in and out, but we don't have to worry about that right now. On the other end, we have a closed system with a moving boundary. This one has a fixed boundary on this end, but now it has heat coming into your system. Because of the heat being added to your system, this piston will move up and therefore will change its properties. Okay, that's all you need to know for now. I'm just giving you examples, okay? A control volume can involve fixed, moving, real, and imaginary boundaries. And let me stop you right here and tell you that the boundaries of the system will be based on your own study as designer, okay? And like I said, I'm just giving you examples of the end of the class, like the end of the semester, based on knowledge that you don't have yet. But just put this in your head that you will learn what is needed in order to define your boundaries. That's it. That boundary or control volume can be fixed, moving, real, and imaginary. Why is that important? Because those fixed, moving, real, and imaginary boundaries are going to help us to define the state of a substance, therefore the energy. Okay, so for now, let's just worry about control volume, and as they could be fixed, moving, real, or imaginary. Okay, moving and imaginary. All right. Why is this important? So I just told you that you need to know how this system could be defined so we can find the state and therefore define the properties that will define the energy. But you don't know what a property is, and that's what I'm going to define now. Any characteristic of a system is defined as property. Some familiar properties are pressure, temperature, volume, and mass. Properties are considered to be either intensive or extensive. All right, so like I said at the beginning of the video, thermodynamics terms needs to be read probably twice. A property is defined as any characteristic of the system. Some familiar properties are pressure, temperature, volume, and mass. Properties are considered to be intensive or extensive. Okay? So let me put it in a simpler words. A property is what will define your state. A property will give you an idea or how your state is right now. Let's just think like somebody is sick, right? How do you know that somebody is sick? Well, probably you will measure the temperature of its body, and then you will determine whether it has fever or not, right? And there's some other factors like the oxygen in your blood and things like that. Those are properties of your body that can dictate to the doctor whether you're sick or not. When you are working with engineering machines, right? If you want to know that the machine is working properly, for example, you have a pump, right? And you check the pressure at the exit of the pump and the pressure is not what you're expected, then you can determine that the pump is not working properly. Therefore, you get into the engineering device, fix the engineering device, measure the pressure one more time until you get the pressure that is needed for the whole system. Okay, like I said, I'm just giving you examples of the end of the class. Okay, but as for now, you have to know that the properties will dictate characteristic of a substance at a certain point. Okay, those properties can be intensive or extensive. Intensive properties are those that are independent of the mass of a system, such as temperature, pressure, or density. Extensive properties are those values who depend on the size or extent of the system. Specific properties are extensive property per unit mass. And again, let's just read it again. So intensive properties are those that are independent of the mass of a system, such temperature, pressure, and density. How so? Let's put it in a simpler words. If you had me before as your professor, you probably know this already. But if you haven't, I always try to make the learning curvature as easy as possible. But at the same time, I need my students to read the book. Okay? These explanations that I'm giving out are just a guidance for you when you read the book. In that way, you will know a little bit, and then when you read the book, everything will make sense. But if you don't read the book and you don't put that effort in, it's gonna be twice hard for you. Okay? All right. So, like I said, intensive properties, they're independent of the mass. So let's say you have at state number 1, 20 kilograms of whatever substance, and then on state number 2, you now have 40. Okay, for each one of them, you're gonna have temperature, pressure, and density, and that will not depend on the mass. Okay, you will always have temperature, pressure, and density for those three, whatever properties or substance you're studying. The extensive properties, on the other hand, they depend on the size. So if you have, for example, state number 1 and you have your piston like that, and then on state number 2 you have your piston like this, right? At state number 1 you're gonna have temperature, pressure, and density. You're gonna have, this is 1, 1, and 1. You're gonna have temperature, pressure, and density. 2, 2, 2. They're independent of the mass. So then when we have the states, right, the extensive properties will expand as the volume is expanding, right? So we have state number 1, the piston is right here, and state number 2, the piston is right there. So the volume will be different as well as the mass. Okay, the composition of this mass will change. Many things can happen, but you have to know that the extensive properties will extend with the change of the size of the system. Okay, so then we have specific properties, and those specific properties are pretty much extensive properties per unit mass. Is when we have an extensive property and we divide it by the mass. So then we're going to start defining very important terms such as density and a specific volume. So density, right, it's defined, and you all know that, sorry about that. So density is defined as mass over volume, and this is kilograms per meter cube. Let me put it right here, much better. Density is mass over volume, kilograms per meter cubed. Perfect. Then we have a specific volume, which is equals to volume over mass. Okay, so these two definitions are quite important because we just started learning new formulas that we're going to be using moving forward. Thermodynamics deals with equilibrium states. So, guys, moving on, we're going to start talking about thermal equilibrium, and everything that it's related to that. because as we move into more engineering devices, we establish that the study has to be in thermal equilibrium, so it'll be like a perfect system, and then we can design for specific circumstances. So an equilibrium is a state of balance. In an equilibrium state, there are no unbalanced forces within the system. A thermal equilibrium is just defined as if the temperature is the same throughout the entire system. So if you have a piston and cylinder, and you want to study that piston and cylinder configuration, then the substance should be the same throughout. And I'm going to show you that with a picture in a little bit. Then we have mechanical, phase, and chemical equilibrium. You're going to keep seeing those, but let's just define those for the best performance of the class. So mechanical equilibrium, if there's no change in pressure at any point of the system with time, that will depend on mechanical devices, as we call them. Phase equilibrium, if a system involves two phases and when the mass of each phase reaches an equilibrium level and stays there. Okay, it's pretty much as you see how the configuration stays the same. A configuration of a substance stays the same, and as soon as it reaches that equilibrium level. The chemical equilibrium, if the chemical composition of a system does not change with time, that is, no chemical reactions occur. So, let's say that we have a system with two states and a closed system reaching thermal equilibrium. So at state number one, we have mass, we have temperature, and we have volume. At state number two, we have mass, temperature, and volume. Why is this important? As you define state number one, you might need those properties in order to start doing calculations. At state number two, you're gonna need the same thing to start doing calculations. So this is the same substance, just at two different states under different conditions. On this one right here is how a system will reach what is called thermal equilibrium, and this is what we study throughout thermodynamics. So you have a before picture right here with different temperatures. You have a temperature right here different than this one, a little different than that one, and different throughout. And then when you go to the after picture, you study the whole system as it's the same temperature everywhere, and that's how you treat your substance before you get into the whole analysis of the exercises. So the thermal equilibrium is something that we always assume when we move into, deeper and harder exercises. And this is very important, guys. Well, I've repeated that it's very important, probably like too many times right now, but I want to go with this. Every time I sign something, it's because it's gonna be whether on an exam and a specific homework or something like that. So it's better that you pay attention to these definitions. So the state postulate, a number of properties required to fix the state of a system, is given by the state postulate. Before we read that, I'm gonna repeat that again. The number of properties required to fix the state of a system is given by the state postulate. And what does he say? What does that state postulate mean? So pretty much it's a state of a simple compressible system. It's completely specified by two independent intensive properties. Okay, the state of a simple compressible system is completely defined, is completely specified by two independent intensive properties. How so? If you have a state number one, and again the piston and cylinder configuration, and you have a state number two, the question would be, you have the two states presented to you on an exercise. How do I define the state? By definition, you have to know, let's say, two intensive properties, temperature and pressure. If you have temperature and pressure at the different states, then you have your state defined. So the state postulate it just tells you that you need to find two intensive properties to define the state. When your state is defined, your exercise is done. You can move on into the next state. And pretty much thermodynamics is just like a puzzle, okay? You need to get temperature from here, pressure from here, and then start making assumptions in order to define those states that will take you to the end of the exercise. So the whole thing you'll be doing from now until December is gonna be defining states as you move, okay? So, and then we call process and path. A process is any change that a system undergoes from one equilibrium state to another. A path is the series of states through which a system passes during the process. To describe a process completely, one should specify the initial and final states as well as the path it follows and interactions with the surroundings. This is a lot of definitions, so let's just read it again. A process, any change that a system undergoes from one equilibrium state to another. So a process will be pretty much what tells you how the substance is behaving as it moves with the time, okay, from one point to another. The path is what defines the process, okay? It's a series of states through which a system passes during a process. To describe a process completely, right, in order to describe that and fully describe, one should be specify the initial and final states so we can know the path and therefore define, the whole substance behavior. So if you have, like I said, let's just call the piston and cylinder state number 1 and the piston and cylinder state number 2. If you define state number 1 and 2, then you will have your exercise done. Okay, so the process would be pretty much everything that will go from state number 1 and 2, and the path will be the path that this process is following. If you define the states in the path, then you will have your exercise done. Process diagrams, right, plotted by employing thermodynamic properties as coordinates are very useful in visualizing the process, okay? Some common properties that are used as coordinates are temperature, pressure, and volume, or a specific volume. We are going to start defining three important terms that you're going to see throughout the course of the class. One is isothermal process, isobaric process, and isochoric process. So an isothermal process is pretty much constant temperature. So if somebody's telling you that the process is isothermal, they're basically telling you that temperature 1 is equal to temperature 2, it's equal to temperature, let's call n number, okay? 1, 2, 3, 4, 5, 6, 7. They will tell you that. If it's isobaric process, then that will be constant pressure. Pressure 1, it's equals to pressure 2, it's equals to press n. An isochoric process is pretty much a specific volume, right? So specific volume 1 is equals to specific volume 2, and then it's equals to specific volume n. All right? So isothermal, isobaric, and isochoric is pretty much constant temperature, pressure, and volume. So once we reach chapter number 2, this is probably in 2-3 weeks, we're going to start learning how to plot processes like this one. So don't worry about the pictures. Probably you have thousands of questions in your head right now, but what is quite important right now is that you know the definitions and terms. And don't worry, we're going to keep repeating those definitions as we move. Steady flow process. Well, for example, this one, you have to get ready to hear these, probably, 10-20 times in the semester. So the term steady implies no change with time. The opposite of steady is unsteady or transient. So a large number of engineering devices operate for long periods of time under the same conditions, and they are classified as steady flow devices. Pumps, turbines, things like that, they will operate in an infinite or a long period of time, and that's why they're called steady flow devices. So steady flow process is pretty much define a process during which fluid flows through a controlled volume steadily. Okay, it has the same pace, it goes under the same circumstances over and over again. Steady flow conditions can be closely approximated by devices that are intended for continuous operations, such as turbine, pumps, boilers, condensers, heat exchangers, power plants, or refrigeration system. They pretty much work under the same circumstances over and over again. So they go from one state to another, and they keep moving from one state to another, and they repeat that infinitely. Okay? Or most likely until the devices are just, up for service or maintenance. So under the steady flow conditions, the mass and energy contents of a control volume remain constant. So pretty much when you have a steady flow device and this is your system, pretty much as the mass is coming in and coming out of your system, you will assume that there are no losses, and therefore the mass will remain constant. And that, I believe, is the end of the class, or as I call it, the end of week number 1. So let me just tell you again what I just told you at the beginning of the video. Guys, thermodynamics requires a lot of reading. Okay, so reading the book, it's super important. Even though this is an online class and you will have to do your exams from home, I want you to read the book. And I'll tell you why. Because I don't care about a final grade that much. I care more about what you learn in the class. Okay, all the knowledge, as much knowledge as you can take from thermo, that you can carry on to the next class, and that one onto the next one, and moving on. Okay, because you are just starting your engineering career, and my whole goal here is that you take at least a little bit of knowledge that will be useful for the moving classes. Okay, for the coming classes. So, well, thank you very much for your time, and I'll see you in the next video. Thank you.